This is the first non-volatile memory. This flash memory can be used for the USB and handphones, phones, and other mobile devices like notebook, pad, etc., etc. Okay. Now, before the flash memories, only the non-volatile memory was the magnet. So everybody has to use the magnetic tape to store the memories permanently. But let me see. This is the new notebook made by Apple, and the total thickness is about 1.9 centimeters. Okay, and very light and ultra thin. And after Apple, of course, the Samsung and LG make all of this new computers. But Apple was the first who make this notebook very thin. And he got an idea, I think it's Steve Jobs' idea maybe, I don't know. But what he tried to do is, this is the hard disk drive, HDD, which make essentially the notebook thick, because this is the disk where the magnetic informations are stored, and then this is a very fine needle, and it's sensing the magnetic N and S as an information. So this whole thing has to be caged in a very stable manner. It just should be vibration free. Okay. So the packaging itself make the notebook very thick. Now, since the flash memory is a non-volatile, okay, you don't have to use the magnetic tape, magnetic memories anymore. So Apple tried to change this whole thing with a chip, and they call solid state driver, SSD. Okay, and then these are all the flash memories, and each one is in one. Let me see. Not this one, I think. 1, 2, 3, 4. 4 with 412 giga. The capacity is that. So each one, the flash memory, each one has what? 128 gigas. So the memory capacity is 512 giga. That's big enough, right? That's very big. But the problem is, this flash memory cannot be used for the programming. So this Mac has to have this 1, 2, 3, 4 flash memories, which is a 500 giga. And you can see 1, 2, 3, 4, 5, 6, 7, 8 DRAMs there. These 8 DRAMs DRAM chips gives you 4 giga. So each one is 5,000 mega, right? 4 giga, so 0.5 giga for each one. So okay. So as a whole, this computer has a capability of programming 4 giga. If your program is more than 4 giga, then you cannot use this computer. So what it does is it will store some information on this flash memory, which is a 500 giga. Okay, and then if you want to change it or programming it, or whatever, if you want to manipulate anything, then what you have to do is you have to take some of the information from this flash memory to the DRAMs. That's the thing that you have to do first. And then you do the programming, and then you finish the programming, and then you have to move that thing to the flash memories. That's what you have to do all the time, because you have only 4 giga DRAMs. So people has to use this. This is called the Meg Air, okay? Meg Air. The computer name is Meg Air. People has to use this Meg Air as just auxiliary computers. You cannot use the main computer. You cannot use this Meg Air as a main computer because the programming capability is only 4 giga DRAMs. 4 giga maybe is enough for ordinary person, ordinary people, but if you are serious about computing, okay, then the 4 giga is too small. And so you have to expand it to like 16 giga or even 32 giga. That is the maximum you can afford, okay? Very expensive if you want to expand it. Now, you may have a question, why this flash memory is so, integration level is that high, but this the DRAM is, the integration level is so low. And the reason is, this flash memory doesn't need a capacitor in there. But DRAM, as I told you last time, one transistor is connected to the capacitor, and that capacitor is the one who are responsible for the memory of anything. Okay, if you put the charges in there, then the state is charged like 1. And if you don't have a charge in your capacitor, then it can be regarded as a 0. So in a binary system, 0, 1, 0, 1, all depends on the states of the capacitor, whether it has a charge or not. Okay. And that capacitor requires a lot of areas. Capacitor is very much proportional to the area, okay? Directly proportional to the area, inversely proportional to the space between two conductors. But the area plays an important role to have a certain level of capacitance, right? So the integration level has to be very low for the DRAM. That's why you have 8 DRAMs in there, but only 4 giga capacitance. While the flash memories, each one can have 128 gigas. That's what it is. And this 4 blocks is the batteries. So instantly you can have an idea that if you want to make the Meg Air more thinner, then you have to work on, is that it? You have to work on the batteries to make it thin, to make it light. You have to work on some flash memories, non-volatile memories, which has to, because you have to extend the capabilities, programming capabilities. So you need to find a non-volatile memories which has a fast speed in programming. Okay, that's a new materials, new device. And lastly, maybe you can talk about this cover. This cover is LCD, okay? But as you can see, LCD needs a backlight. So it has to be thick. But if you can replace this LCD with the AMOLED, for example, then AMOLED is a self-light emitting device. It doesn't need any backlight. So the display becomes very, very thin. So three things. If you can change the display to AMOLED, and if you can change the battery more thinner than this, and if you can find the non-volatile memories faster than flash memories in programming, then you're going to be a winner in the future, right? Now, let me talk about this. Let me talk about the non-volatile memories faster than flash memory in the programming. Okay, let's turn off. Okay. Flash. Now, in our lab, since 2000, early 2000 years, my lab, electronic materials lab, we have studied on the PZT materials. PZT. That's a lead, zirconium, titanium oxide. Okay, that's a complicated material, but it's a famous perovskite structure material. Perovskite structure. And this is very famous in ferroelectric materials. Ferroelectric means it can store the dipole energies. So if you have PZT here, and then if you apply the electric field to this material, then it has a dipole aligned to this according to the electric field applied. And then if you remove the electric field, then it stays there like this. That is the ferroelectric properties. Okay. So if you can use this PGT materials in the MOS structure, then this is the source and drain. And if you use the PGT materials here, and then put the gate in here, gate. So in the normal MOS structure, you just replace the gate oxide with the PGT. That's all that you have to do. And you apply the threshold voltages to the gate, then PGT may be aligned, the dipoles will be aligned in one direction. And then if you remove that, the gate voltages, then it just stays like this. So that it's exactly the same to the situation that your capacitor in the DRAM is charged. Okay? In order to erase the information, you are going to apply the reverse voltage to the gate, and then this dipole is going to disappear. It's going to disappear. Okay? So now if you can make this thing, okay, we call this FRAM, and if you can make this thing, then the programming speed is almost the same to the DRAMs, because the structure is almost the same. And as I told you last time, in the flash memories, the problem is this has to have a 2-gate, right? Source and drains, and then the first floating gate is going to be sitting. This is the floating gate, and then you need another oxide gate insulator, and then you are going to have a gate like this, and then you are using this tunneling phenomenon, tunneling or emission, electron emission phenomenon, so for the flash memories. So in this flash memories, essentially the working principle is essentially different from each other. Okay, and the important thing is this programming speed should be the same to the DRAMs in this FRAM. Right? That's the important thing. Now, the problem is if you have a bulk material of the PGT, then it shows a very good ferroelectric properties. But if you form into a thin film to be applied for the integration and transistor fabrication like this, then the grain boundaries in a PGT, since it is contains so many elements in there, the thin, if you fabricated these materials in the thin film, then the grain boundaries kills everything. We call that fatigue, retention, okay, and the leak. All those things are related to the grain boundary characteristic. And since the oxide is in there, okay, that grain boundary property is terrible. Like ordinary, you can see in the ordinary metallurgies, if you put some oxygen into or carbon into the metals, then the metal becomes brittle, right? Just like that. So this PGT, if you fabricate it in a thin film, then the grain boundaries kills everything. So even though people have been known this perovskite structure PGT is very good for the ferroelectric properties, it has a very good ferroelectric properties, they cannot apply this material into the transistor fabrication, FRAM fabrication. Now, in my lab, what do we have found is that if you put a platinum, we don't know why, if you place the platinum dot in the PGT amorphous film, of which thickness is about 1,000 angstrom on that level. Okay, you sputter the PGT on the glass, then it's certainly an amorphous. Okay, and then you deposit the thin film of PGT like a 100 angstrom or 500 angstrom, just like that. Because PT platinum is very expensive material. So you deposit the same film of PT on top of PGT, and then you pattern it to get a dot here, and then you apply the temperature like just a 500 or 600 around there. Then what we have found is that it grows a single crystal, no grain boundaries. To a certain level. So if you put the dots like this, for example, then it shows a square of single crystals. So only grain boundaries you can find is in these lines, where the growth has been is to meet. Okay, so we call this technology as the SNLC, selectively nucleated lateral crystallization. Okay, and then we place the platinum very close to this PGT, and then make a single crystal, and then pattern it, and then we put the gate on top of it. Then we are going to have a PGT thin film without the grain boundaries, and we can have no grain boundary effect like a fatigue, retention, whatever leak. Is the excellent properties we can have. We can have excellent properties. So now we come to know how to make an F-frame. Now if you apply this F-frame technology to this Mag Air or thin notebook devices, then you don't need the DRAM anymore. All you have to do is you can have a 500 giga programmable memories in hand. It has a tremendous effect in the industries. Why? Because Samsung and LG, they are very good in making non-programmable memories, like flash memories, DRAMs. They are so good in there. But for the programming memories, they're so poor. In other words, Intel and other foreign companies, they are very good in those programmable circuits and things like that. So, but if you use the FRAM, then the storage memory and the programming memories is combined. So you don't have to separate those things. Now a lot of people get a lot of money by just making the circuits specifically designed for specific devices. Now, if you use the FRAM, the memory business and non-memory business, they are all going to be combined. Then you're going to impact a huge impact on the industries. Okay, so anybody who are interested in making FM, contact me. I'll let you guys know. Now, the rest of the chapters in chapter 1, the rest of the section is planar technology there. And let's see. The key technology improvements for the VLSI, the 1, 2, 3, 4, 5 technologies has been introduced there. You just read it. And if you want to know details of it, then you can refer to the undergraduate course. Okay. And the future trends, that's trends, still the trends. And the next section is planar technologies, essential steps for the MOS transistor fabrication, and essential steps for the bipolar transistor fabrication on page 56. We just refer to those things, and then you just take a look at it. And every literature, you can find easily the literatures concerning on this, the fabrication technologies and things like that. So it's not going to be discussed in detail in this class. Okay, and the next chapter is the junction properties. Anybody has a question? Let's see. We talk about the junction properties. Let's begin to junction properties next time on Monday. Okay. All right. So I'll see you on Monday next week.